On rare occasions, we get to witness moments of sheer genius. This is not one of those moments. Warning, severe facial and monitor damage alert is in effect. Get out those oven mitts. Push the monitors back out of punching range. And let's light this dumpster fire and have some fun.
Well, forget about that, right? But Robotham, Flat Earth Society guy, gave everybody the first square function, right? QE's come along and give the new generation the inverse square, the square root.
Now, if you think he's talking about the square and square root functions being inverse operations of each other, he's not. He's talking about the inverse square law. And he thinks the inverse square law means the square root. This is unbelievable. You guys are going to enjoy this one.
So we're going to go over this now, but in on the level type way of thinking, just a think tank, right? Open think tank.
Open think tank, huh? Meh.
About something that's been around for years, this argument. Now, it states, if the Earth is a sphere with a radius of 3959 miles, P, then, and this is the then, like the consequent of that, right? With a little bit of math. So it says, then the horizon distance measurements must be, underlined, no more than to 1.225 times the square root of the observer's height in feet. Q. What's everybody else understand about it? I mean, this argument has been around for a while. QE and Nathan Oakley have obviously talked about it quite a lot. Flat earthers are meant to be number one flat earth proof for a couple of years at least. Why is it that nobody really understands what 1.225 times the square root of the observer's height in feet actually means?
And I think you're right, Bev. I think the trick is making sure that people can't understand it by translating it to an actual calculation. And then I think it exacerbates the problem by letting them off the hook by saying it's algebraic. You can't really understand it because it's algebra math, when the claim is actually geometrical, which is far easier to understand the implications of geometry because it's pure logic.
The only one thing that I found out recently is a lot of people saying, I don't understand maths. And the reason they don't understand maths is because people like you, Paper, have said, well, it's just algebra. But that doesn't help anybody understand what 1.22 times the square root of the observer's height in feet has got to do with anything.
Well, since you guys couldn't be bothered to type 1.22 times the square root of the observer's height in the Google search bar, I did it for you. Google comes up with 336,000 results in about a half a second. So it's not like this is exactly hard to find. But let's go through it. Now, you said Quantum Eraser gave this to us, Bev. Quantum Eraser didn't give this to us. Pythagoras gave this to us. That formula is easily derived using the Pythagorean theorem, and it works like this. Line C to D is obviously a tangent line to the surface of the Earth. The observer is up there at point C. The tangent intersects the Earth at point D, and radius line A to D also intersects at point D. So by definition, that radius line and that tangent line have to form a right angle. We now have a right triangle, Bev. The length of one leg is D, the length of the other leg is R, and the length of the hypotenuse is R plus H, H being the height of the observer above the surface. The Pythagorean theorem tells us that d squared plus r squared equals r plus h squared. Now, if you just do that little bit of math I've done on the left side there, you get d equal to 1.225 times the square root of the observer's height, and that is if you're using imperial units. If you want to use metric units, it's 3.577 times the square root of the observer's height. There's nothing mysterious about it, but the problem with that modus tollens that Quantum Eraser came up with is simply that this formula does not consider refraction. This is what would happen if the Earth had no atmosphere. The Earth, of course, does have an atmosphere, and the atmosphere causes refraction, and that effectively increases the radius of the Earth. So you can't take this pure geometric calculation and compare it to an observation that you make through the atmosphere. And there's no simple one formula that's going to work under all conditions because these things happen. This is what the oil rigs in Quantum Eraser's Black Swan look like on a normal day. About 20 feet of the bottom of the oil rig on the right is being blocked, but about half of the one on the left is being blocked, and they're being blocked by the curvature of the Earth. But on a different day, when you have extreme refraction going on, you'll see a thing like this, where the horizon is some indescript distance beyond both of the oil rigs. So that's the fallacy in the modus tollens, Beth. But the formula is correct for a pure geometric calculation. I think it's safe to say that you can no longer claim you don't know where that comes from.
The square within the inverse square law is something optical.
Now you're bringing up the inverse square law, Bev. And the inverse square law has nothing to do with calculating the distance to the horizon or the drop from horizontal. The inverse square law applies when some form of a force or energy is evenly radiated from a single point in 3D space. If it radiates from a single point, it expands like a sphere. The surface area of a sphere expands by the square of its radius. Therefore, the intensity of that energy at the surface has to decrease by the square of the radius. In other words, 1 divided by the square of the radius, hence the term inverse square law. Now, light certainly behaves that way, but so does any other form of electromagnetic radiation. It could be gamma rays, X-rays, radio waves. All of that obeys the inverse square law, but things that don't have anything to do with light or electromagnetic radiation also behave by the inverse square law. For instance, Newton's law of gravitation is an inverse square function. Coulomb's law for electrostatics, the same thing. Sound radiating in a gas. All of these things behave in accordance with the inverse square law and have absolutely nothing to do with optics or light. So 1 divided by r squared is not the same thing as the square root of r. Right, Bev?
Right?
Yes, absolutely.
It's an optical square that's seen over a distance, and it's about how much light can pass between a distance.
Yeah.
It's just working the opposite way, right?
Yes, but this is essentially the same. So when he is talking about this distance to horizon, these calculations are derived from the Robotham calculations.
Which is optical.
No, Paper. Now you're talking about a formula that approximates the drop from horizontal over distance. And Robotham didn't come up with this. Surveyors had been using this for many, many years. Again, just like the distance to the horizon, we can work this out with the Pythagorean theorem. If line AC and line AB are both radius lines, 3,959 miles in length, and C to D is approximately the same as the surface distance for the arc from C to B, and that's roughly true for short distances or distances up to 100 miles or so. And if we assume h is roughly perpendicular to line CD, which is also true for very small angles, then h is equal to r minus the square root of r squared minus d squared. Do the math, and that is 8 inches times distance in miles squared. That's where that comes from. But don't give Robotham credit for this. He's not the guy that thought it up. That's for sure.
No, Robotham calculations are not up to.
What do Robotham's calculations come from? Come on, give us that.
Only from
The dreams that you had.
I think it was he wrote that his calculations are from, I think I don't remember in which book, but he's writing this in Parallax.
You could do so. You want him to do you so much you could do anything.
He took from proportion 45. I don't remember where proportions are in Euclid. And he took proportion 45 from which book I don't remember. And this proportion is about curve, very similar to sphere. And some part, this is irregular.
Would it be fair to say that Gladys knows more about this than the try-thinking think tank? Boy, I hope Gladys didn't hear me say that. Thanks for watching.
That's all, folks.